and addresses, fixing globals and addresses, and maybe pointers. Okay, this is looking good. Looks like we're ready for a little stream. Looks like we're ready for a little stream. It's gonna happen. It's gonna go. All right. All right. We're all good. I don't think there's anything else to do. It's all here. Hi, I'm Tom and I talk about code. Welcome to another Rust live stream where I'm building my compiler. Today we're working on global variables. Last stream I left them broken. Today we're going to go in and fix them. I think they're broken because my code, I changed where code gets loaded, essentially. So we're probably going to have to think about this and fix this. Maybe in more than one place, we'll see. But basically the test that broke is not the test that I was testing. So the test that I wanted to pass passed, but as another test has failed as some kind of secondary effect of what I was doing, which isn't great. Let me just make sure my mic is nicely adjusted here. If we get everything working, we're going to jump across and try pointer types, because there's actually a lot in common with pointers and globals. Pointers represent a value in memory. Well, global variables, they're kind of like, the way I'm handling them in my language, and especially if you watched the last episode, if I can remember how to draw an ampersand, there it is. So if you have like an address of a variable and you kind of dereference it, well, I mean, a global variable that's just stored at some address, it's kind of like a pointer that is automatically dereferenced. That'll hopefully become apparent as we look at the code and dive back in, if that wasn't clear before. Okay, so this is literally the screen I left the last stream on. I haven't moved, I haven't turned my computer off, I haven't done anything here. That's a lie. But we have a test that fails, and the test is like randomly the inline assembly test, and that's the only test that fails, which means that the test that I wanted to, unless it just stops. Okay, maybe all the tests fail and we just did this one first. It looks like we have only done a few tests. So why does this fail? It fails because we've hit a zero instruction. And why do we hit a zero instruction? Well, what does that mean? That means we're trying to run an instruction. Like, zero is not a valid instruction, right? I have intentionally set up my machine so that an instruction of all zeros is invalid and it crashes the machine. If you jump to a region of memory that is uninitialized, that is just zeros, you're gonna crash. You're gonna crash early rather than a bunch of garbage happening and just getting the wrong answer or looping forever or something stupid, right? It just dies. So, why does it die? Why does it die? Test compiler 20. Okay, yeah, so we load our code. Let's walk backwards from what this test is doing. Test common. We load our code at the offset of the program, the start offset of the program. Now, do you know what's probably a good idea? We have this function I wrote to format and print out our context. And the whole point of this was to make it easier to see what was going on when we had errors. Well, let's continue this trend. Let's continue to enrich this display, because it's actually a really useful visualization. Debug printing it, there's like a bit too much detail here for debug printing to work nicely. So let's add global at self.dog. So we want to be able to visualize the address that our global start at, and the program starts at program start offset, and I can already see what the problem is. Let's go back to our test code. We load in the program words at, we load in the program at an offset, right? The bytes of the program gets loaded at some offset. But we don't set the program counter, so that's a problem. After we do this, after we do our unsafe, funny 16-bit to 8-bit cast, we actually need to VM set register PC. We need to set it to program start offset. And now this is going to work. Okay, it doesn't quite work because I wrote my code wrong. But other than that, it works, and it works really well. Make T. Okay, excellent. Excellent. U16 found U32. That's cool. The program counter can only be 16 bits. We have a 32-bit address space, but the program counter can't utilize all of that space. The program counter can only point at the first page of memory. This is a very deliberate trade-off. Okay, so we hit an infinite loop. Why do we hit an infinite loop? Again, this is a little bit baffling to me. This is so strange. So now we just have some garbage offset for the start of the program. And I don't understand this either, because the program start offset, it's supposed to just be offset by the number of globals, but we have no globals. Let me also fix this so that we have new lines after these, because at the moment it looks ugly. It's visually hard to digest. And the whole point of writing this stringer for a context, this formatter, was to make it easier to digest. So we're going to do that. We're going to do that. So what is going on? If we look at code gen, we can see where we set this program start offset equals program offset. Program offset, global page size. Global page size. So if global map is empty, which it is, we can see that it is, the global page size should be 0. It follows that it should be 0. And then the program offset should just be at the, oh, hold on. I hard coded this, didn't I? That's really dumb. That's really dumb. That is very, very dumb. Okay, so I need to do two things. The first thing is, this is actually the offset plus this. No, it isn't. No, it isn't. Global page size. The global page, no, it isn't plus an offset, because we have a base. Okay. Offset, offset. The offset gets passed through. The offset gets passed through. So what we want to do is go to where compile is called, so main. That's the wrong main. Main, lang main, bin lang, there it is. Sorry, it's not called main, it's bin lang. Compile, loaded program offset, this is 0. Okay, so that's correct. That checked. I suspected we were passing 1 0 in here, but that's correct. So then let's do this again. And let's think about what's going on. What does this context say to us? It says the globals start at 0, which is good, and the programs start at 1 6. Where does this come from? This is 1 0. Where does this come from? Where does this come from? How could it be coming from anywhere? Because there are no globals. I can see there are no globals. So this offset is 0. Oh, because I've got instructions before. Okay, hold on. So program offset actually needs to be before this. Let's say program start offset is offset plus global page size as U32. The start of the program is here, and then we start writing code after this. This program offset represents we're actually writing code, but we start with some code already in the program. We start with this, which is our initialization code. Okay, so now if I make t, it's going to work. And, okay, it still doesn't work, but at least this test is the test we expect to be failing. That's good news. That's very good news. We're trying to set this to 2, and it's still getting set to 53,626, which isn't ideal. Okay, that's maybe not optimal, but we can deal with that. Test, what's it called? Global left, register A. This is all okay. I think what I really need to do is step through this. So I'm just going to quietly in the background start up my web server. And we'll run this, we'll step through it in a debugger, we'll see what's actually going on. All right, let's pull this in. This example program's a little bit different than what it was before, which is cool. It actually shows you like doing some arithmetic. Okay, so let me copy this program and I'm gonna paste it into test.code. I think this is the same code anyway, but I'm gonna just copy and paste it to be sure, because I wanna make sure that I'm testing the right thing, right? That makes sense. And then we're gonna cargo r lang test.code. We're gonna pipe this to the disassembler, and that's gonna dump out all the instructions. Then we're gonna copy this to the clipboard. Excellent. Okay, so we paste this in, we build it, and now we can start stepping through. So let's see what happens. Let's see what happens. In PC18, this is where we're gonna jump to, Now this no longer has to, this now has to load at a different offset, right? Right, because if I go back, what is it, lang test global. If I test this, we can see that program starts at 2. The program starts at a different offset. The program starts at a different offset. So we need to tell the thing this, build. Okay, now this starts at 2. Now we have the correct memory padding for our globals to be allocated. This is important. This is important. We're going to step through. So we set up the stack pointer, we set up some stuff, we jump to main. Okay. In main, we grow the stack because we have local variables. We load the value to, this is what we're going to try and set. If we have a look at our program, if we have a look at our test.code program, we're trying to set test to the number 2. So this is where we load to, we step over here, we end up with C, yep, with the value in the C register, that's good. Now, MB0. This isn't correct, obviously. Oh, no, actually it is, because our first global should be at address 0. So we're trying to say, store at address 0, the address in B, which is 0, whatever's in C. So this should store 2 in C. That's good news. That's very good news. Now we're going to see us try to load this. Load word C0. Why do we do this? This isn't right. Right? This is where we get garbage in the C register. And now if we run, we're probably going to see this value in the A register at the end. Yeah, exactly. Okay, so that's it. That's really simple. That's really, really simple to fix. That is, so it's an add, oh no, it's a load, what is it? Store, load word. Everywhere we have a load word. Local, here, C. So here we want load into register C, the memory address from B. This is what we want. So now if I build and copy this, go back to our edit, we're going to see the instruction is going to look a little different. Load word CB0. I think that's the correct instruction order. I do always need to check this every single time, which is a good sign that my virtual machine is probably a little counterintuitive to use. Load word. R1, R2, yeah, so we store in R0. The first register should always be like the destination. Okay, so if I run this, we get 2 in the A register, which is what we expect, because we're now not dereferencing the number 7. Excellent, excellent. So now if I make T, it's gonna work. Everything passes, everything's happy. We have global variables. They work, we can assign to them, we can read from them. This is good news, this is good news. Is there anything else we need to test with a global variable? Can we assign, so let's go to our globals. Let's do a slightly more complicated thing. Let's have 2 globals, global int test and global int foo. We'll set test to 2 and we'll set foo to the value of test. Let's actually make this a more interesting value. Let's set it to 82. Foo is going to be the value of test and then we're going to return foo. Okay, so in some senses it's a very simple program, but it is going to highlight if there's any issues between these things. I suspect this will pass. Except I need to give it a different name. Two globals. I guess that makes sense, right? It's two globals. Call it two globals. Left equals right failed. Okay. Because we're checking for the wrong value. Now it passes. Beautiful. So that's good. That's really good news. I'm happy with that. Let's commit it. Let's ship it. Lang source. Add global variables. Perfect. All right, that's in main. That's done. We can't undo that. That's a permanent, that's a one-directional change. That's done. That's written in the logs. That's written in the history. So what's next? That was way quicker to check off than I expected. So let's check it off, because that's my favorite thing to do. I love checking things off lists. Pointer types. Is it time to start thinking about pointers? I kind of alluded to this before, right? But there's this funny relationship we have with these globals. Like a global, at the end of the day, a global, the way we've defined a global, let's call it G, it's an address and a type for what is stored at that address, right? It's two things. So when you have a global X and you say X equals 4, this is really like saying, hey, here's an int star, which is, a pointer to an int. We'll call it A equals, and let's just say adder for the address. And then we're going to say assign to the value at A, 4, right? Does that make sense? So global variables are essentially pointers that automatically dereference. That's all these things are. We could implement these without this nice little bit of compiler sugar, right? We could implement these as just pointers. So we actually have the code for storing values to an address and loading values from an address. That's kind of what I'm getting at here. These things are kind of related. So this is like global land. And then this is like the real world. This is kind of what really happens. If that may, I don't know if my drawings are ever useful. If you're watching this video and you think my drawings are useful, please let me know. If you think they're not useful, also please let me know, because man, it would be good. It would be good to know. Okay, beautiful, beautiful. So let's do it. Let's do it. Let's make a branch for this, because this is going to be big. And one of the biggest things to do is going to be going into our AST and significantly changing the way types work. Because now we're going to have a pointer type, which is a reference to a type. And this has to be wrapped in a box. You can't leave this just on the floor. It has to be boxed, because otherwise Rust is going to blow up. Because if you just do this, a type now is a thing that contains a type, but a type is a thing that contains a type, which is a thing that contains a type. This thing effectively has infinite size. So you need to wrap it up in something on a heap, a pointer, in fact, to break that reference. Beautiful, beautiful. So now, from string for type, this is harder. This is harder. This requires more logic. Indeed, we can no longer just from string a type. We need to write a parser for it. So this has to go away. Okay, I can keep the import of the trait, but I have to get rid of that. It's a bit tragic, but I have to get rid of that. Okay. We're gonna need some more expressions as well. We're gonna need unary ops, right? They're like bin ops, but they're not. So. I'm just realizing that the left-hand side of this equals is going to be a bit trickier than I thought. But we can do the right-hand side. The right-hand side of everything is great. The right-hand side is very, very easy. The expression part is super simple. So let's go into our language, and first let's write a parser, parse type. Okay, so we already have this function. First off, these aren't alpha characters anymore. We want this kind of alpha symbol function. Alpha. Let's say pub fn alpha. Actually, this is like the inner type, right? The inner part of a type is the repeated character, but it may optionally have one or more stars out the front. Okay, so let's try and write that. Let's say let's say repeat. Let's say optional. I think it's called optional. Do I not have an optional combinator? That's a bit of a... Allow empty is close. Actually, allow empty, yeah. TE. Allow empty. That makes more sense. So a type is just a series of stars followed by... Actually, no, it's crap. I'm gonna make the star part of the type and not part of the variable name, because in C there's an important distinction between the two, right? In C, you write the type and the pointerness are separate. So you have int, and then you have star A, and because you can also have star B and declare multiple things that are pointers, you could also say int, or you could also say, let's say short A star B C ... right? Where only this one's a pointer. This is how C works. It sounds insane, but this is how C works. In my world, I think I'm gonna go with the prefix star where I say int, right? Pointer to an int. Perfect. Do I want to get into the world of double prefix star? Maybe. Maybe for now it's just enough. Well, but because it's got this recursive structure, why not just nest these indefinitely, right? So it's a star followed by a type. That's the thing. So it's this. Parse error. Whoa, that wasn't quite what I wanted. So it's this, but we say let s equal skip white space token. So it may be a star, but we need to match on it. So we want to say match if we have some. If we get one, then we want to we want to say it's type pointer inner. This is a nightmare. Parse type. So if we get a star, then we try and do this recursively on the rest of the input, which is S in this case. And we unwrap this, because if we're doing this, this is where we do the error return. Oh my gosh, this is confusing. This is already confusing. But we do this. We say, okay, we give back the rest of the input and a pointer to whatever the remaining type was. If we get an error variant, we ignore it and we try to parse the type. Parse type. And this can probably go inline, right? We don't need this anymore. We can just do this. Okay, so then we try and do the same. We try and parse differently starting from here. Okay, that works. That is a recursive, that is a very recursive parser combinator. Okay, what happens when I build this? It probably yells at me, right? It probably blows up for a lot of reasons. Pointer. Ah, okay, so there's other stuff. There's other stuff that's happened. First off, we haven't worked out how to print it out, how to display it, and that's easy because it's just star t. What else do we have? Mismatch types. Token, input. Oh, oops. Okay. It's not. I always mix up my optional and my error variants. Always get them mixed up. And then this function isn't called that anymore. From stir. Now this. Yes. Hold on. This. It's not a star, therefore. It's kind of tricky, isn't it? We want to maybe say parse type raw maybe. Let's give it a silly name and just write it, and then we'll work it out. Result stir. It's still going to be a parser, right? It still makes sense to make it a parser. I probably could have kept this as a from stir function, but it doesn't seem right making from stir not complete, right? We need this whole parser combinator structure to make this make sense, in my opinion. So we'd have this inner function, which says match input. I think I'm allowed to match like this. Void. Oh yeah, I was. This is what I was doing before. So void goes to okay. No, wait, I need to use my existing structures for this. So I can go any new. Oops. I just changed the mode of my keyboard. Hopefully that won't have any strange side effects. It already has. Oops. So any. Okay. This is actually tricky. This is kind of annoying to work out, right? We kind of want to say map token, but I feel like this is going to be this thing where we can't actually make a vec of these. We'll try. Void. If we get void, then we want to map this to why is that? All right, yeah, because of this. If we get void, we're going to break this to type void. And if we get int, we want to map this to int. And then we want to say p.run, p.parse input. So if I build this, it's going to yell at me. For multiple reasons, actually. But so then we say parse type raw. Oh no, it's just this, and it's just this. And actually, it's just this. And actually, we get a parse error now, so now let's do that. That makes more sense. Okay, so let's see what happens here. Once I do this. Void. That also makes sense because actually I don't think I need braces at all, right? If they're just one statement, one expression, I think that's fine. S0 not found in the scope. That is actually what I meant to do. Cool. There we go. That makes more sense. You can tell I'm hungry. Yes, now expected closure found a different closure. No two closures have the same type. Yeah, so I think we're running into this thing where they don't match. What about this? What if I wrap it up in curly braces? I think this is the same error, right? I think I just can't do this. Yep. Okay, okay. Super Cricket, my keyboard has a speaker in it. Yeah, this is a plank. No expense spared in the keyboard department, except I bought it secondhand off a guy I worked with. But yeah, no. It has a music mode. Hold on. Which one? I'm gonna get distracted by this because music mode. Where is it? What's the key map? Okay, I can't find what the shortcut is. I'll play music one day. I should do a music stream. That would be fun. Maybe 1,000 followers. I'll do a music stream. I've been saying it for years. I can't do this. So what do we do? I mean, I guess I do what I was doing before, right? Where I say match input void. The problem is this isn't extensible because sometimes we're gonna have things. Well, I guess it's what I had before, right? How much do I have to undo? How much do I have to undo to get this? Okay, so let's start with this, right? Let's start by parsing the thing. Alphanumeric. It's underscores still illegal. We iterate over it, we collect, that's fine. So then we match on the result. That's what we do. That's how we marry this match statement with parser combinators. That's what we do. So we match AST type void. Anything we get here is an OK response. So we have whatever we didn't parse, and then the result of this match statement, except it's as a tuple. Perfect. Void goes to void, int goes to int, car goes to car. And then at some point we're going to support the user supplying their own types, but not yet. Okay, expected string found stir. Yeah, that's cool. So we want to match res. No? Can we not do that? What? Can we not just infer that this is a stir slice? Okay, what's going on? As ref, there we go. There is a way to do this. There's always, in Rust, there is always a way. There's always a way to make the type checker do what you want. Expected result found this. Yes. Because I want to get rid of the cursed semicolon. Value not covered. That's okay. We're going to have to make a corresponding pointer type here. Gonna have to make a corresponding pointer type here, which is again going to be the same thing. It's going to have this recursive structure because it points to, like it's a pointer to a thing, and a pointer is always. That's going to be really hard if I do full 32-bit. I'm going to keep these as one word rather than two words for now. But and maybe there'll be two separate types. Maybe I'll have like a short pointer type and a long pointer type. That might make more sense. To do long pointer. You know, the 16-bit era is freaking wild. 16-bit code, it's hard, okay? Like, you don't have much memory. And so you have to do paging, but then like paging with the C memory model is weird. All right. So long pointer, something for the future. We don't care about it right now. The size of a pointer is 2. If we are printing out a pointer, then we print out star t. And if we're converting from a pointer, we do the nested conversion, except this needs to go in a box, new t.into. All right, beautiful. We're close. We're close. This field does not implement copy. No, it doesn't. We can't copy once we have this structure. And now this is going to create issues. So we're going to have to say self.clone and other.clone. Right? Which is really freaking annoying. It's really, really annoying. The trait from box AST type, yeah, well, that's because we have to dereference the T before we into it, I guess. But, do I have to wrap it like that? Return type has type which does not implement copy. So we just have to clone. We just have to clone everywhere. T.clone. Clone everywhere. Clone all the things. Clone all the things. And now we build, and now all our tests will still pass, and there will be no problems with this whatsoever. Except for this one that failed. Okay, apparently... support user types. What type could we possibly have? What has happened? Int car void. Did I do void? I think I did. I think this is just me being really silly. Let's put the thing in here. No, sorry. Res. What type has caused this to blow up? ASM. Yep, cool. So, that's because we've attempted to do this in the wrong order. Inline ASM now has to come first. We try inline ASM first because because this thing inline ASM lang test. Oh yeah, I don't think I moved this to its own file. If we try and parse this as a type, we're gonna blow up. So we have to try this first. Make t. And now we're fine. Now everything works. It's okay. It's okay. This now has to go before this. It's fine. Don't sweat it. Don't worry about it. Now it works. Perfect. Okay, so we can model a pointer. I'm surprised this didn't break in more places, honestly. I'm really, really surprised this didn't break in more places. I guess we don't really, we have to construct a pointer, we have to factor them into expressions somehow, but we don't, because it's just a box that a number goes in. So it's the same as everything else until we get to the unary operators, right? Dereference x and address of y. Until we do this, pointers actually, they're just numbers. This is C. This is how C works. This is why C is cool. I'm gonna take this opportunity, now that we've modeled them in the type system, to take a short breather and check on the wonderful pot of lamb neck soup that I have on the stove. I'll be back in a moment. All right, we're back. We're focusing in. My soup is delicious. I've done very well. I think I'm a pretty good cook, but today I've really outdone myself. You know when you make a soup and it's just like milky, like garlicky, it's more of a broth, I guess, but it's delightful. It's really delightful. Okay, so we have pointers, and now we probably need to add the unary operators that make pointers tick. Now, currently I have a binary operator type. Do I want a unary operator type? This is a good question. Let's make them distinct expressions for now. So, also taking the address of something is weird. Like the address of a global, we just return the address, so that's going to be easy. And for args and args and locals, yeah, we can work this out. We can do this. This is easy. Super Cricket says skin. This is soup chat now. Skin forms as soon as you turn the heat off on your last stew. Good stuff. Yeah, I've been making so many stews. It was like 9 degrees in my house yesterday when I was streaming, which wasn't good. I don't recommend that. That's too cold. That's when people like get sick and like people die. By being don't put rust in soup. I try not to. I've got a good quality enamel coated pot. It keeps all the rust out. That's actually true. Okay, I'm faffing around. I'm getting distracted. I'm getting distracted by soup, which is a fair thing to get distracted by. I haven't had dinner yet. It's getting a bit late. Okay, so let's add address of. An address of. Hold on, I need to add it up here. What am I? I'm getting ahead of myself. Address of. And this is going to be address of expression. Maybe. Actually, no, that doesn't make sense, does it? Because you can't have the address. What can you take the address of? I need to make myself a table, okay? So, address of x. Address of x. That's a really ugly color. Address of x. Yes, this is fine. Address of x plus y. Not fine. That's not a thing, right? This doesn't go anywhere. This is just a calculation. Address of foo, the function call. No, we can't do that. That doesn't make any sense either. Address of foo, the function. Yes, I like that. I think that would be a good thing to support. Variable args globals. Yeah, that sounds about right. So actually, yeah, this is only valid for very few things. So it's gonna be whatever a variable is. Let's just say string. Screw it. It's one symbol. It's one thing. We can take the address of a thing. Maybe it's an identifier actually. I'm not sold on the value of this identifier type, but we'll stick with it for now. So add self address of. And this is where we do this funky character. Cool. Do we need to do anything else with this? Yeah, of course. There's going to be a bunch of things that break. Okay, so when we get the type of something, this is good. This is good. This is good. This is going to look a lot like getting the type of a variable, except we'll just wrap it up in a pointer. Address of. I guess I should call this name for consistency. We're gonna do this. And it only works for certain things. We'll keep it simple for now. We won't do... Actually, we will do symbols, because that means we do functions as well. So we have type, pointer, box, new, type, int. Cool. And this we want to say type, pointer, box, new, and we just wrap this up in Like, because this is just an expression, we can just wrap it up nicely. That's cool. You should be able to get the address of types or namespaces. You shouldn't be able to get the address of types. Yes, no, of course. Yeah, namespaces don't exist. I don't know if namespaces ever will exist. I might honestly just make the executive decision that this is a language for small code, where you don't have enough things going on that you need a namespace. That's my kind of vibe right now. I would like to write a better language in the future. Maybe that compiles to this machine. Maybe that compiles to a more interesting and applicable platform. But, oh, hold on. I've just thought of something else. I don't know if we can take the address of a const, because I don't think they actually exist anywhere. They just get they just get compiled in. So let's mark this with a to-do as well. To-do. What do we do here? Perfect. How do I build this? It probably yells at me about something, right? Expected stir found identifier. Address of. That's. We have to do this. Excellent. Symbols.get name. That is because we have to do this. How do consts work in my language? Right now they don't. You can't define a const, but I have some machinery internally for handling them. I think if the code generator encounters one, it crashes. But the idea is that they just get compiled into the program, right? They're not actually variables. They're literally just like the compiler knows what a const is. The program doesn't know it's a variable at all. It's just a number that gets baked into the binary. Baked into the binary at every point it is referenced. Fun fact, because of how stupid loading values might take 3 instructions, I'm not sure if that's actually more efficient than putting them in a variable. It replaces the const identifier with its value. Exactly. Every const value, they can only be 16 bits. You can't have a const bigger than 16 bits because it's a 16-bit virtual machine, even though we might have 32-bit addresses. They're actually, a 16-bit address and a 16-bit page, so we'll deal with that. If maybe missing an else clause. We are missing something here. Else if. Oh yeah, we need a final else. Else, we don't know what the hell this is, and it's actually just going to have type void. The address of something unknown is going to have type void. Or maybe it should actually panic. Maybe this actually is a panic. Cannot take address adder of name. We can't do it. It's impossible. Okay. Now in CodeGen, we need to work out what we're doing here. This is also going to be fun. This is going to get very unwieldy, this compile expression. It's going to get very, very big, very, very quickly. Can't take an address of a literal, that doesn't make sense. Rust does const the same way, that makes sense, as opposed to static, which Rust is a variable. Yeah. Again, I think I'm gonna avoid the word static. I think that's gonna be the best place for me. Okay, so address of, we have to be able to get it. So if let some variable that we get from the scope if there's a variable defined with this name in scope, we match against it. If it's a local variable, and it doesn't matter what the type of this thing is, that's the interesting thing. We just grab it. Static should be avoided. Good. Okay, I'm glad we see eye to eye on this. Yeah, just like function scoped variables, like they're just confusing. There are cases where it's useful, but it's always confusing. I don't know. I find it confusing. I find it. There are cases where it's useful. You can usually build a different abstraction, and I think the only cases where you don't build a different abstraction are when you're severely resource constrained. But like, I don't know, that you're not my target. This system is severely resource constrained, but not in that way. Not in the way where you need to make bad language decisions to support it. I'll make my machine better rather than add static scope. Okay, so if we want to get a local, we want to grab and this is actually going to be very much the same, right? It's basically the same up until where we do the load words. So, whoops. We're again going to push this to the stack because everything currently goes through the stack. We're going to make it smarter at some point, but not right now. So instruction, we get the base pointer, we put the base pointer in C, we add this magic number to the base pointer, and that's the address. That's what we load from in a later instruction. So we now just need to push this to the stack. And again, we're going to copy and paste because I'm lazy. Stack push, yeah. So it's the same as what we do when we actually reference the value. We just don't get the value. We just get the address. Excellent, excellent. Okay, that's good. That's cool. Block variable. If we have an arg, this is going to be the same thing. Again, assuming that things only exist in the first page, which in the case of, like, basically I've made the assumption that all of my code and the stack live in the 0 page. And I don't think it makes sense to put them not in the 0 page. Arg, we're going to do the same thing. Oh, except we can't do the same thing because we use load stack offset. So this is actually going to have to look a little bit more like this, except we're going to subtract. So we load the base pointer and then we look at what we do for load stack. This is basically an instruction for getting args, right? This is our special add to a thing and load. And maybe I should call it add and load instead, right? It takes a register, it subtracts. It actually subtracts from it. Maybe I need an add and load and a sub and load. I don't know. They're very useful instructions. We subtract a word offset times 2. So what is our arg offset? For arg I, it's I plus 3. So we want to add immediate signed new, I think it's signed, -1 times I as U8 plus 3 times 2, or maybe it should just be -2 times. That makes more sense. New checked from signed. Cool. So we do the subtraction and then we push that address to the stack. Beautiful. And now global, this is my boy, this is my favorite. If it's a global, then all we have to do is, okay, vec. We load the address into an immediate, which I think I wrote a helper function for. Load address 2. Yes. Okay, so we say we need to wrap this up in a block. And again, I'm probably copy and paste is even smarter than this. We say, yep, load address 2. And we probably actually want to say, I don't know, yeah, B and M. I guess this one's harder because this can't necessarily go, well, but again, like the way a global allocator works, right? 0, out dot push. We do this. We add another stack instruction. We want to put this in C because C stands for clobber. This is the register that we just mess around with. And then we return OK out. And that should work. That should be, yeah, perfect. It works perfectly. There were no compiler errors. There were no problems at all. Okay. Trait neg, oops, hold on. I as I8. That fits better. That fits better. Okay, found here. Expected, found, expected result vec found blah. That's because we need a default case. Yes, Okay, we need to do this old thing. We're gonna say to do. This is my new favorite macro. I love this to do macro. I think Vibane, that was you that showed me this yesterday, right? Address of var type var not implemented. Cool. So now this will build. Block variable cannot be. Have I really not? Oh, wait, hold on. It's because I need this. I'm pretty sure I implement debug. Yeah, cool. Okay. Now we have to do the else case. And again, I'm gonna borrow from here. Expression, variable. What do we do? Variable undefined. We're gonna steal. We're gonna borrow. To string. Awesome. Okay, so now we should be able to get the address of a global. Let's try this. Let's lang test pointer.rs. Let's borrow from here. I'm doing a lot of borrowing today. It's very fitting when you're writing Rust and doing a lot of borrowing. Okay, adder of global. Let's make a global. Let's say let int b equal let int star int b equal address of test return b. There we go. That's all we want to do. That's all we want to do. And we expect this to be 0 because the first global should go at address 0. And what happens? It probably blows up and yells at me over some stuff. Yeah. Parse error, blah, 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 blah. Okay. Negvorsa, hi. Welcome. Welcome. Thanks for stopping by. This is Rust Madness. We're getting some big parser errors. Okay, so adder of global panicked. Why? Why did it panic? Where did it panic? Void main let blah 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 expected to. So this is okay. It's not passing this as a valid function. And it's really because of this, right? So this is going to give me the wrong answer. No. Huh. Adder of global. What? Oh, obviously. Do you know what happened? Do you know what happened? This one's funny. What happened? Excuse me. What happened is I didn't implement this. I didn't add this to my. I didn't add a parser for this. So expression literal blah blah blah. So we need an expression adder of. I'm probably going to get this working and then go have dinner because I can really smell the soup now and I'm getting hungry. Beautiful. Okay, address of. So we want to try and grab. We want to grab again, if you're new to this, this is my wonderful written out manually written out monad. We want to grab skip white space token. We just want to grab the exact character of this. And then we want to try and grab a variable. And we don't want to skip white space, actually. We want to just put this. Actually, maybe I just want to say map identifier and do it this same way. AST. Actually, no, it's just an identifier, right? It's just an identifier. I was actually overcomplicating that. We can just use our identifier parser even. It's not even a combinator. And then all we do is hand back expression address of name. Okay, S1, this, beautiful. Now let's add this to our big list of expressions. We need to do this before a variable, right? Otherwise we'll just match with the variable first. What kind of lang? This is a C-like language. This is C, but worse. And I called this adder of for some reason. I'm going to call it address of, because that's what I've called it in the struct. The enum, I'm pretty sure. Address of. Okay, what's wrong? Nothing? Okay, that's cool. Pointer. Did that just pass? I think we're good. I think we're cool. Global int foo. Let's see if we can get the address of foo, which should be at 2. Oops. I want make t. And that passes as well. Okay. This is pretty good. This is pretty good. I'm very excited by this. Wow. We can get the address of things. We can do it. It's happening. This is a big step. This is such a big step. I'm impressed by how simple that was. I thought that was going to be a lot harder, but I guess when you have C-like semantics and everything's just a number, pointers aren't actually that complicated, okay? You heard it here first. You can quote me on that. Pointers aren't actually that complicated. On that note, I am going to go eat because, like I mentioned, I have a gigantic pot of soup waiting for me, and I think that's a good place to leave it, with something working. Looks like it's towards zig then C. Yeah, I think there's a bit of zig in there. There's a bit of just languages that are C-like in there. Some things that have improved on C. I see someone who's making a movement shooter. Now, I hate the word movement shooter, but I'm a big Quake fan, so we're going to raid this person, obviously. Buildzoid. Let's have a look at what they're doing. Single player. We're going to raid this person, all right? So we're starting the raid. Throw some love over to this guy. Seems like cool stuff. Hypervelocity, I think it's called. That sounds awesome. Thank you everyone for stopping in. Good to see some regular faces. This has been a bit of a shorter stream, but hopefully soon we'll be back doing even more awesome pointer stuff. I'm Tom, and I will see you next time.